we move to future Earth. Come on, please. Lawrence devised a chaotic water wheel and that replaces a mathematical model of atmospheric fluctuation with a mechanical model. The equation is like this. So push. So glass balls are falling above and start rotating. I'll count 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So, glass ball are holding at a constant speed from directly above asymmetry of the field and unsymmetrical motion began. It is similar to vibration, but not a constant vibration. Nor is it completely random. While it is called chaos, it is generally within a certain range of oscillation. So, if someone were to draw the graph with this rotational angular velocity and position of its center of gravity of water field, a figure like a butterfly spreading its wings will be drawn. Like this. It is often said that Lorentz discovered the unpredictability of weather, but rather he taught us that by repeating calculations with slightly different initial values and processing them statically, a calculation will converge to one value or transmission between multiple values. An example of transition between two values is come here, Milankovitch cycle or glacial interglacial cycle. There is a two state and the shift, and almost periodically. And another example is 9 months forecast of El Nino La Nina event. Repeating calculation with the slightly different initial value is called ensemble calculation. It is used for daily weather forecast in 2 weeks forecast and typhoon forecast for 5 days. Here is an example of a long-term forecast, 9-month forecast of El Nino La Nina, compiled by IRI, International Research Institute of Climate and Society. Here, there is a 17 dynamics model, and 9 static models are participating. Above of horizon axis is El Nino model, and below of axis is La Nina. Each line of models are ordinary ensemble calculations that repeated many times with one model. X is actual observation data added later. So no one knows the reason, but there is observation data in middle of bunch of many lines. Average of these predictive models is called multi-model ensemble. Average and observation are very good. So next month, also observation data is middle of bunch, middle lines, and also middle of lines, the average. So no one knows the reason, but multi-model ensemble is very strong. But 2015, yes, I said please remember the observation data is out of lines. The next out. So very deviate from average. So very big El Nino, super El Nino occurred. El Nino. And back to average. So now observation data shown in average. Also average. So multi-model ensemble is very strong, but sometimes prediction is wrong. The multi-model ensemble continued to be out of sync for 10 months until 2016. This period corresponding to the end of hiatus, which I show you first. Perhaps the heat that had been building up in the ocean while the temperature rise were stagnant was suddenly released. As you can see, even multi-model ensemble can sometimes be way off, but over the long term, some errors are smoothed out. For this reason, scientists believe that even if it is difficult to predict in 5 or 10 years prediction, but 20 years to 50 years prediction may be possible in some extent. In order to make this long multi-model ensemble prediction, come on please. First, temperature and volcanic activity and sun activity and greenhouse gas level in the past 2000 years will be reconstructed. And next, create a climate model that can take into account the effect of volcanic activity, solar activity, and greenhouse gas concentration. And next, optimize the climate model parameters so that the temperature of the past 2000 years can be reproduced as much as possible with this climate model. Finally, with the parameters, long-term multimodal ensemble prediction is performed by, there is so many, I can't count, but very large number of multi-model ensemble. Then, future projection depend on carbon emission scenarios in the future. On the left graph of this panel, carbon emission were projected under 5 scenarios from here to here, and SSP 1.9 is for 1.5 degrees Celsius rise. Carbon neutral should be achieved in 2050. And beyond that, carbon capture exceeds emissions. SSP1 2.6 is for 2 degrees Celsius rise, and is also a severe reduction to the carbon neutral by 2075. The future temperature projections in these cases are shown in the right graph. The runaway warming cannot be stopped except by the 2 scenarios below. Shown here, temperature rise depend on carbon emissions, and although CO2 only accounts for 20% of the greenhouse effect, by reducing CO2 emissions, water vapor feedback can also be suppressed, and thereby limiting future temperature increase. Finally, why should we choose the most severe carbon emission scenario? This figure compares the rate at which species can migrate with climate velocity. It means the rate at which global warming will shift suitable areas for species. Considering the northern hemisphere, the more rapid global warming is, the faster climate velocity. Each species' optimal habitat will move northward, and species cannot move faster than the climate velocity without human assistance. This red line shows clearly that if we hold 2 degrees Celsius rise, even this will not allow some species cannot catch up with the climate rate, but at least we must keep it below this line. Back to the previous graph, to keep below 2 degrees Celsius, we would have to make such a severe reduction, even capture the CO2. If reduction will be taken earlier, we might not have had to reduce so severely. The deniers, I said first, have succeeded in delaying the reduction only to make it seem that global warming is still controversial. As long as the deniers are still active in the future, this struggle will be getting worse. That is all of my today's presentation. Thank you.